So today I'd like to sort of work on finding missing values. Now, of course, this table that I've shown here doesn't actually have any missing values, but we want to assume for the purpose of this video that the underlined values are actually the values which are missing. So just imagine this table for each sample here, and we have three. For each sample, that the number which is underlined is actually the number which is missing. So we're given values, but there's also a missing value that we have to solve for. So what is the context here? Well, the context is that we're given three different samples of hydrogen chloride. And of course, we know that within a particular sample, if we have hydrogen and chloride, then of course a certain percentage of that sample will be hydrogen and another percentage of that sample will be chlorine. So in the first sample here, we're sort of imagining that we have this hydrogen chloride sample, and 52% or 52.9% of that sample is hydrogen, and 47.1% is chlorine. And of course, we're given also their gram equivalent, in other words, how much they are in grams. So in this sample, 0.312 grams is hydrogen, and the mass of chlorine is 0.278 grams. So what this tells us is that what this table tells us is really it's given us three values here, but this third value is essentially the value that we want to solve for. Now I've given this value here, but we want to be able to derive this value. And I want to sort of express two methods by which deriving this, the mass of one while given the information of everything else we have, why this is intuitive. So let's just assume, and actually let me try maybe even to cover it up somehow. I don't think that I can, but let's just assume that this is not here. So we have hydrogen chloride, right? And this is sort of the first example here. This is the first method, so to speak, and let's see. So this here is the first method. So I'm going to call this method one. And the first method, essentially, we know very well that we can make ratios between products and reactants and products, and perhaps reactants and reactants. For this one here, if we can have a ratio. We can say that you know, 52%, 52.9% is hydrogen, and 47.1% is chlorine. In other words, for every 52.9% of hydrogen within the sample, we will have a corresponding 47.1% of chlorine. And of course, this makes sense because 52.9%, if you have 52.9% of something, then the remainder of that, out of course 100%, will be will just be however much percentage is remaining to get to 100. So this makes sense. But in order to really work with this, let's go ahead and convert these to their decimal equivalents. And 52, any percentage for 52 included, 52.9% included, any percentage is over 100. So you could write the percentage this way, or you could write it equivalently as 52.9 over 100. That's really what it means because the percentage is out of 100, right? And so if you're dividing by 100 in order to get the decimal equivalent here, what you want to do is you want to move your decimal 2 places to the right. If you were to multiply by 100, you want to move it 2 places to, well, if you multiply, if you multiply, you want to move it 2 places to the right. And if you divide, you want to move it 2 places to the left. So 52.9 here, if we're dividing by 100, we're going to move that decimal point 2 places to the left, and we're going to get 0.52 9 over 100. Or actually not over 100, because we've already taken into account the fact that there is a 100 present. So it's actually 0.52, 529. That's the decimal equivalent. So what we actually have here is 0.52, 9. And of course, if we were to apply the same logic here, it stands to reason that we move the decimal places 2 places over 2, and we'd have 0.471. 47.1. And of course, this wouldn't be a percentage. We already took into effect that this is out of 100. So for every 0.529, for every 0.529 of hydrogen, we will have a mass of chlorine, which would go for 0.471. And this is, of course, out of 100. So in this case here, we can divide. So this is hydrogen, and this is chlorine. And we always want the ratio to be expressed as 1 is to something. In other words, here we have 0.529 is to 0.471 chlorine, which I'm assuming is grams. But we want to say that, okay, for every one of hydrogen, how much chlorine will we have? That's a conversion factor, right? And so what this will allow us to do is it will allow us to actually solve for what we're trying to solve for. So what we can do here is if we divide both sides by 529, we're actually keeping the value of the ratio the same, or the fraction, because the ratio is a fraction. But I can divide both sides by any number, and the value will still be the same. You just have to simplify it down to get back to the original value. So we can say that for every 1 hydrogen, we'll have 0.471 divided by 0.529 of chlorine. And if you were to actually go through this division here, you would have 1 gram of hydrogen, right? 1 gram of hydrogen, and this division would essentially give you 0.890. So you'd have 0.890 for chlorine. So now we know that for every 1 gram of hydrogen, we need 0.89 or 0.890 grams of chlorine in order to satisfy the sample given this proportion, in this percentage. And so this is sort of a conversion factor, right? I mean, if I told you, okay, well, if you have, let's say, 8 grams of hydrogen, how much chlorine would you have? This is why we make this conversion factor. If we know how much of one we have, and then in, of course, relation to the other, then we can just magnify that proportion on any scale. So really, the question now is, okay, if I have 1 gram of hydrogen and 0.89 grams of chlorine, for every 1 gram of hydrogen, I have 0.89 grams of chlorine. If I up the amount to 0, or if I actually reduce the amount, if I have 0.312 grams of hydrogen, how much chlorine would I have? Right? So what this does essentially is it lets us talk in terms of grams. And when we're talking in terms of grams, we can, of course, like I said before, magnify, or even in this case, sort of think about a lower quantity. We're setting up a proportion, basically. So for every 1 gram of hydrogen, I have 0.890 grams of chlorine. And if I had 0.312 grams, if I had 0.312 grams of hydrogen, well, how much chlorine would I have? In grams, of course. And of course, this is, again, a conversion factor, right? I mean, if I asked you, right, and this is sort of an example, if I gave you a conversion factor and I said that for, if I said, I have 500 meters and I want to go to, how much is it in kilometer? Well, how much is it in kilometers? Well, what you do is you'd realize that 1 kilometer equals 1,000 meters, right? Which is why it's actually called kilo, because kilo means 1,000. So you could make a ratio here. You could say that for every one kilometer, it's 1,000 meters. And then you could, so this is essentially your conversion factor, right? I mean, this is, it's sort of analogous to what we have here. So for every kilometer, you have 1,000 meters, right? So can you find 500 meters? Well, you take what you want, which is 500 meters, right? You take what you want. And between this conversion factor, you just check, well, what do I want it to be in? I want it to be in kilometers. So let me go ahead and put that here. And of course, you'd have your meters down here, because your meters would eventually end up canceling out. So you'd have 1,000 meters. And your meters, and this is of course in kilometers, your meters would cancel out, right? And then you just do a basic problem of arithmetic. You do 500 divided by 1,000, right? And that would be equivalent to your kilometers. So sort of simplifying this down here, you get 5 over 10, which is just 1 over 2, which is just 0.5. So really, for every 500, so for 500 kilometers, 500 meters in kilometers is essentially 0.5 kilometers, which makes sense. Because if 1 kilometer is 1,000 meters, then 500 meters is going to be half of a kilometer, which is 0.5 kilometers. And so that's how, setting up a ratio, a conversion factor can actually help you. And that's what we've done in this example. That is what we have done. We've said that for every 1 gram of hydrogen, just as we said for one kilometer is this much meters, we said 1 gram of hydrogen is 0.890 in chlorine. And then we set up a conversion factor. Well, how much is 0.312 grams of hydrogen? Well, we do much of the same approach. And we'll do here is we'll say, okay, well, I want this is what I want to find, right? 0.312 grams of hydrogen. And I want it in terms of its chlorine equivalent. And so what you do is between this conversion factor, you put your grams aside so that it cancels out with your hydrogen, right? And of course, you want it to multiply with what you want it to be in. You want it to be in chlorine. And so what you do here is you have your grams of chlorine in this case, and your grams of hydrogen would cancel out, and you'd be left with having 0.312 of your it's no longer hydrogen. In fact, the hydrogen is sort of canceled out, and it's going to be multiplied by 0.890 of chlorine. And of course, if you were to do this multiplication in a calculator, you'd eventually get 0.278 grams of chlorine, which of course is the answer in this case. Now, this is sort of a method where you make a ratio between your reactants, sort of in terms of their percentage, and then you figure out for every 1 gram of hydrogen I have this much chlorine, or for every 1 gram of this I have this much this, and then you can then go on to find out how much chlorine you'll need for this much hydrogen. And you could go the other way around. You could say, well, okay, if I had this much chlorine, how much hydrogen will I have? And you do the same conversion factor, and that would get you to the same spot. But one interesting point to note is that maybe we didn't have to go this route. Maybe instead of dealing with the percentages, maybe between making a ratio of the percentages, we could instead make a ratio between the grams, right? And that's ultimately what we did down here, right? We reduced it down to grams. And so if you were to go jump straight to the grams, you actually couldn't do that, right? Because you're not given the amount of grams, and so it's very difficult in order to do it this way. And so for the next example here, actually sort of sticking on the first example, I'd like to teach you another method, which is perhaps a little more tedious, but it does broaden the understanding of what we're doing here with ratios and fractions and percentages, perhaps. The other thing here that you could do is you could use this formula, which is the part over whole equates to the percentage over 100, right? Percentage in terms of its numerical value, and I'll get into why I'm saying numerical value in a second. But this is sort of another method. If you had another approach, if you were thinking about this in a different manner, then this would sort of be your approach. Your approach in this case would be, okay, you're looking at these values here. You have your percentage, and you have your mass in hydrogen, but you want your mass in chlorine. How do you do this? Well, the thing is, imagine if I told you had the full amount. You'll notice that you don't have the full amount of the sample, right? You know that hydrogen takes 0.312 grams of that full amount of the sample, but you don't know how much chlorine takes, and that's really the whole purpose of trying to figure out how much of the total is chlorine, right? So if we were to find out the total first, right, and that's sort of, if you were to find out the total, right? You know that 47.1% of that total is chlorine, right? And so if you had the total, you could just ask yourself, okay, what is 47.1%? What is 47.1% of the total? And so instead, it's attractive. It's an attractive proposition that if we just find the total, then 47.1% of that total will in fact be your mass of chlorine, right? If 52.9% of that total in grams is hydrogen, then 47.1% of that total will be chlorine. So in this case, what we do, I mean, you have, you can total, they're sort of synonyms in this case, total and whole. You can use both interchangeably. In this case, I use whole. So this is sort of the proportion that you have here. And if you can solve for the whole with working through this proportion, or you could solve for the part, and you'll see later on why the part becomes, we're going to use all three in different cases. In this case, we want to solve for the whole because we know that in the context of this question, 47.1% of that whole is going to be your chlorine. So what we'll do in this case here is we'll say, okay, well, part of the whole, I know part of the whole, it's 52.9%, right? And that's part of the whole. Or you could say 47.1% is part of the whole. But in this case, your percentage, as per this formula, the percentage really goes here. This is sort of a numerical quantity. Of course, percentage is also a numerical quantity, but it's sort of, we're looking for either decimals or whole numbers. So in this case, you could say that, okay, well, I know that, I know hydrogen, right? Hydrogen is part of the whole sample. So hydrogen 0.312 grams is part of the whole sample, right? And it's equal to, well, what is hydrogen equal to in terms of this, in terms of its percentage? Well, it's 52.9%. But of course, you don't want to add the percent here. You're just looking at the numerical quantity. So 52.9% over 100, that's the over 100 part is sort of an indispensable part of this formula. And I'll actually tell you why, but what you're doing here when you're looking at this formula here, you're looking at, okay, what do I have? I have a part, I don't have the whole. Do I have the percentage? Yes. So if you have the percentage and you have the part, then of course it makes sense to fill these in and just solve for the value that you don't have. 100 is not going to change. So that's just an indispensable part of your formula. So what you'd end up doing, and you don't want to put the percentage here, right? Because 52.9, if I say 52.9%, this itself equals to 52.9 over 100 because a percentage is out of 100. So it doesn't really make any sense to do 52.9% over 100, right? That doesn't make any sense. So 52.9 itself is out of 800. So you don't want to put that percentage there. You're expressing this 52.9 out of 100. So that takes into account for the percentage sign. This is just so you can not work with percentages for arithmetic, but instead work with decimals. And so what you do here, I mean, you have a proportion, and the famous rule for proportions is that if they are a true and valid proportion, then you could cross multiply. So in this case, you could do 100, right? You could do 100 multiplied by 0.312 grams of hydrogen equals, and of course, multiply here, W multiplied by 52.9. And of course, what you would do is you'd solve for 100. I mean, you'd solve for W in this case. Now that really, when you're here, there are different routes depending on how you want to approach it. You could say that, okay, W is equal to 100, right? And then multiplied by 0.312 grams over 52.9, right? That would get you the answer. You could say that, or you could instead just multiply here. You could just say, okay, well, if I multiply anything by 100, especially if it's a decimal, only if it's a decimal, you want to move it to the right 2 places instead of the left. Remember how I said that if we're dividing, then we'll move it to the left. But if we're multiplying by 100, we'll move it to the right. And so if you do that, you'd actually get 31.2, right? Because you'd move it 2 places to the right, divided by, and you'd obviously have to move that 52.9 to the other side. And since the multiplication here, it's going to go into the other side in division, so you do 52.9 equals the whole. And the idea here is that both of these should give you the same answer. Because it's essentially the same thing, right? I mean, you're instead of having the 100 here, you're just saying, okay, well, 100 times 0.312 is just 31.2 grams, and then you already had the 52.9 to begin with, and so if you were to plug this into a calculator, you would in fact get your answer. So you can see that if I were to do 100 and then of course multiply that by 0.312 and divide that by 52.9, I'd get a particular amount. I'd get 0.89. But if I were to do this here, if I were to do 31.2 divided by 52.9, then I'd get much of the same thing. I'd get 58.9. So it really doesn't matter, right? I mean, you could go about it either way. But for the purposes of moving forward, we know that the total, or the whole in this case, as we used it, is 52 point. Well, it's not 52.9. It's 0.589. So it is 0.589 grams, right? That's the total. And I mentioned before that 47.1% of the total is in fact going to be chlorine. So if I do 47.1% of 0.589, then what I can do here in order to work with it in arithmetic, I can convert this to sort of a fraction, right? I can work with fractions. I could do 47.1 over 100, right? That takes into account that the percentage sign is there. And of in mathematics means to multiply. So I multiply in this case, and I do 0.589. And if I were to do this, then this would give me a particular answer. But what I want to tell you here is that instead of doing this, what you could do is you're dividing by 100. And when you divide by 100, you move it 2 places to the left. And so you could do 0.471 multiplied by 0.589. Or of course, you could stick with this if this is making more sense. These are both equivalent forms. So if I were to do this, if I were to take 47.1, and if I were to do 47.1 divided by 100, and I were to multiply that, I multiply that by 0.589, then in this case, I would get 0.278 if I were to round it. But if I were to do the same thing here, if I were to do 0.471 and multiply it, right? I could multiply it by 0.589, then I'd essentially get 0.278, or the same answer. So if we go back up here, we actually acknowledge that 0.278 is in fact the mass of chlorine. So that is essentially how we would do this particular one, and we'll move on to this one here. So as we continue here to the next sample, of course, we want to ignore the underlined parts. So it would be the mass of hydrogen, and mass of hydrogen in terms of its percentage, and the mass of hydrogen in terms of its grams. We want to sort of ignore those, and we're only given the mass percentage of chlorine and the mass of chlorine in terms of grams. So what we're given here in this case is 65. Well, let me just go ahead and say that that chlorine in terms of its percentage is 65%. Or actually, it's a little more precise. It's actually 65.4%. And of course, the mass of chlorine, the corresponding mass of this sample, is going to be 0.555 grams. So the chlorine in terms of its grams is going to be 0.555. Now, of course, compared to the first sample where we actually had three known values and just one unknown value. In this case, we have two unknown values and two known values. Now, I'm gonna sort of propose two methods here, and in case you don't entirely get to the first method, there's always that other method, and the same goes for the second to the first. So for this case here, you know, it's a little more elusive. We want to understand that we have a particular sample, and if this, so we have a particular sample, and 65% of that is, so maybe if I were to say 65% of that is, in this case, it is going to be chlorine, right? It's going to be chlorine. And we know that out of 100% of the sample, so this entire sample is out of 100%, 100%, if 65.4% is chlorine, then the remainder, of course, must be hydrogen. The remainder must be hydrogen. So all that other stuff is hydrogen. So if you were to think about it that way, then it could be easy to think that, okay, well, if 65.4% is chlorine, then the hydrogen percentage is going to be 100% minus 65.4. Of course, the remainder. And if you were to do this, you would essentially get a particular number here. You get 34.6%. Now, if you hadn't realized that, there's another way, right? Sort of a backdoor way to get this information. But for the first method, if you did in fact understand that the remainder must be hydrogen, or the remainder of a particular sample, if we're given the percentage, let's say 50%, then the other 50% must be the other element that the sample consists of. So in this case, we're actually not, you know, in this case, you know, we know now that hydrogen, the hydrogen in terms of its percentage, is 34.6%. So it's not controversial anymore as to what the percentage of hydrogen is, but of course we want the corresponding we essentially want the corresponding mass for hydrogen. We know the percent, but we sort of want the mass. Now, if you remember in the first example, what we did was we made a ratio. We essentially made a ratio between the percentages, and we moved our way up from there by using conversion factors. But if you were to do the same thing here, I mean, that could work, right? So chlorine to, if we have 65.4% chlorine, right? And the ratio here is 34.6% of hydrogen. Now, of course, we want to deal with decimals and whatnot. We really can't perform arithmetic on percentages. So what we'll do is we'll 0.65 for 0.65 for is chlorine, and we'll say that 0.346 is hydrogen. So that's sort of the ratio that we have. But remember, we always want it in terms of 1. And so in doing so, let me just go ahead and take care of this stuff down here. In doing so, what we can have is we can divide both sides by 0.654 and eventually come about to having 1, and this of course is chlorine. For every 1 gram of chlorine, we will have 0.346 hydrogen divided by 0.654. And this, of course, will be hydrogen. So for every 1 gram of chlorine, we're going to have this amount. And if you were to divide this amount, you'd get 0.529 grams of hydrogen. So for every 1 gram of chlorine, we have this much hydrogen. And so it's sort of simple then to find the mass for hydrogen, right? We can use, again, a conversion factor. We have a conversion factor present. For every 1 gram of chlorine, we have 0.529 of hydrogen. So if I want to express my, I know the mass of chlorine, so let me go ahead and start with that. I know that the chlorine mass is, in this case, it's 0.346 let's see here, 0.555. So 0.555 of it is chlorine, grams of chlorine. And you think that when you're looking at this conversion factor, you want your hydrogen, right? And so you want your chlorines to cancel out. So you're going to put your 1 gram of chlorine down here, and your chlorines would cancel out, but you want it in terms of its proportionate amount of hydrogen that it would read. So you'd actually put 0.529 grams of hydrogen here, and your chlorines would cancel out, and now you're left with 0.555 grams multiplied by 0.529 grams of hydrogen. And of course, when you multiply this out, you're going to get your hydrogen equivalent, and your hydrogen equivalent would essentially be 0.294 grams of hydrogen. So you'd actually have 0.294 grams of hydrogen. So again, it's just comparing the decimals, making a conversion factor in terms of 1. And if you have one of them, you can always find the other. And we could have went the other way around, right? We could have said that, well, if I have this much hydrogen, 0.29 of hydrogen, I could find the amount of chlorine. And let's see, in this case, so my purpose here is to tell you that this conversion factor is really at the heart of everything. If you have one in terms of something else, you can always find the other thing. Now, what we did here was we had the mass of chlorine, right? We had the mass of chlorine, and we were able to make this ratio. But what if I went the other way around? What if I said, okay, for every 1 gram of chlorine, I have 0.529 grams of hydrogen, right? And if I know how much hydrogen I have, will I come back to this much chlorine, right? So in this case, I figured out by the ratio that I have 0.294 grams of hydrogen, and I have this conversion factor. So can I go from hydrogen to chlorine, right? So if I have this much hydrogen, will I have this much chlorine? Well, let's see. So let me go ahead and take how much hydrogen I have, 0.294. And this, of course, is hydrogen in grams. And I want my hydrogens to cancel out looking at this unit factor. So 0.229 grams of hydrogen, and I want it to be in chlorine, so 1 gram of chlorine. So these hydrogens will cancel out, and essentially what I'll be left with is 0.294 over 0.529. And of course, doing this division, you would in fact get 0.555. So it really works. I mean, if you have this conversion factor, you can figure out how much hydrogen you'll need or how much chlorine you need. So this approach here is really effective. So we have, but of course, back to the original problem here, we figured out that 0.294 is our hydrogen, right? That is our sort of our prime amount here. And but of course we want the percentage. Now, for the percentage, you know, it would be nice to say, okay, well, 0.294 grams of hydrogen, 0.294%, no, 0.294 of the total, right? Of the total would be hydrogen, right? If we could find the percentage that 0.294 reaps of the total amount, that would essentially be our way out here. We'd have the mass of hydrogen, or we'd actually have the percentage. Well, we'd have the percentage of hydrogen. How much percent of 0.294 of the total is hydrogen? But of course, it's apparent that we probably want the total in order to even do that. And so if you essentially want to do that, well, let me just go ahead and say that we already figured out the percentage, 34.6. I'll leave this part for if you can't figure out the percentage. So we already have 34.6 as the percentage for hydrogen, and we already have 0.294 for the mass, and that's essentially accurate. But what I want to go off on the side and tell you is, what if you couldn't figure out Or what if you glossed over the fact that if you're given the mass of chlorine, then the remainder will be hydrogen? What if you glossed over that fact? What if you weren't able to come to the percentage of hydrogen? How would you then go about doing this? And the answer is, I mean, you could look. So if this didn't work out, you could look at the part over whole formula there. You could say that, okay, the part over the whole equals the percent number over 100, right? You could look at that, and you could essentially say that, okay, well, you could say that, okay, well, the part, right? I have a part here. I have, let's see, I have the chlorine, right? I have 0.555 is a part of the whole. The whole, I don't know. It'd be nice to know the total. So your approach here is just to find the total. Well, let's just build our way logically here. Your goal is to first find the whole, and then just say that and then so firstly, the whole, and if we were to just build this logically, and then maybe I'll talk about what we would do from that point. But the whole in this case would essentially be, so you don't know your whole, so just let that be W, equals, and so your chlorine, you know that 0.555 of chlorine actually ends up being 65.4%. So 65.4% would be chlorine, but you don't want the percentage, you just want the number. Over 100, right? And this is, of course, your chlorine in terms of your percentage. And so this will essentially give you the whole if you were to do the algebra here, right? You could do 100 multiplied by 0.555 chlorine equals W multiplied by 65.4. And then, you know, your W, if you were to transpose this to the other side, your W would actually end up being 100 multiplied by what you had here, which is 0.555 over 65.4. And this would essentially give you a proper answer, right? I mean, you know that if you multiply 100 times anything, that just becomes 55.5 over 65.4, because of course you want to move the decimal place 2 places to the right. And then if you were to do this, you'd essentially get the whole as being 0.848 grams. And that is essentially your whole, right? So you have your mass of chlorine, which the table gave you is 0.555 grams of chlorine. And you know, you have your whole, right? What is the total mass of the gram or mass of the substance, which you just solved for, which was 0.848, right? 0.848 grams. And you want to figure out, basically, how much mass of that is hydrogen. Not its percentage yet, but in terms of its grams. Just keep moving forward with what seems easy, basically. So the law of conservation of mass essentially tells us that if I have chlorine, right, if I have a particular X amount of grams of chlorine, and I have to add, and well, the thing is, like, if you have a particular amount, let's say I had hydrogen chloride, and the amount was, let's say, 80, right? Then, you know, hydrogen would have to be a particular amount in grams, and chlorine would have to be a particular amount in grams. And both of these would have to add up back to 80. And that is the only way you could have hydrogen chloride of 80 grams. If you have and that's essentially what the law of conservation of mass says, is that if you have a particular amount of any particular element, and you add that to another element, the addition of their mass, which in this case is grams, should be the product's weight in that sense. So in this case, you know, chlorine is 0.555 grams of chlorine, plus whatever amount of hydrogen we're talking about. It must add to 0.848, which is the total amount, right? And so you could just think of this as being X, right? And then you could solve for your X amount of grams of hydrogen as being 0.848 grams of your total minus 0.555 grams of chlorine. And if you were to do this here, you would figure out that your hydrogen actually comes up to being 0.293 grams of hydrogen. So now you know that your chlorine amount was 0.555 grams of chlorine, and you add to that 0.293 grams of hydrogen, and you essentially get 0.848 grams of your total. And so that is the reaction that took place here. And so now that you have this known value, we can go back to saying what we wanted to do before, which was say, okay, well, 0.293 grams of hydrogen, how much percent of that, or how much percent of 0.848 grams is 0.293? And so now we're left with a question here, how much is X of Y percent? Or how much percent of, let me sort of phrase this properly. How much percent of 0.848 is 0.293, right? And this again would sort of be, you have two options here. You don't have to rush into anything. You could do the part over the whole, or you could do another method, which is a little more straightforward. But the part of the whole says that you use the formula part over whole equals the percent number times 100. In this case, we have the whole, and we have the part, and we have 100. So we want to solve for the percent number, right? You're just plugging in things that you know, solving for things that you don't. And so the part in this case is going to be 0.293 over the whole, which is 0.848, right? And that is, of course, your whole. This is your whole, and this is 0.293 hydrogen, right? Equals the percentage, right? You want the percentage. You want how much it correlates in percent. Well, we'll leave that as X percent, and you have 100 here. So if you, again, we have a proportion, we can cross multiply, things work out. So 0, or 100 rather, if you multiply that to 0.293 equals X percent of 100, right? That's just, or 0.848, I'm just cross multiplying in this case. You'd eventually try to solve for X percent, and you'd say that, okay, well, X percent is equal to 100 multiplied by 0.293, and then of course that's divided by 0.848. Now, of course, when we multiply anything by 100, we move it 2 steps to the right. So X percent is actually equal to 29.3 over 0.848. And if you were to do this, let's see, 0.293, and let's see here. If you were to do this, let's see how much you get. You would essentially get 34.5, right, in terms of your percent. So your X percent in this case is 34.5%. And if you go back, we found the mass of hydrogen. We already said that it was 0.293, or if we round it, then it would be 0.294. But now we found the percentage. And so, of course, the percentage, if we go back to this table, 34.6, which is, of course, if we round 34.5, we get 34.6. And 0.293, which if we round that, we get 0.294. So this is clearly a way that you can sort of solve these problems by sort of comparing part over whole, this formula, or really just thinking about it a little logically. And if the logic doesn't strike you as apparent, then you can always go for the formulaic approach. It's sort of an algorithm in a way that sort of lets you solve for these unknown values. Now for this next one here, I think it's much of the same approach, to be quite honest with you. It seems like we have 15.8% of hydrogen, 0.2604 grams of hydrogen as well. And we want to figure out sort of these corresponding the mass of chlorine and, of course, the mass percentage of chlorine. So let's just go ahead and discuss those two approaches that we talked about before, where we have the mass of hydrogen, and we have the mass percentage of hydrogen, and we have the mass of hydrogen in grams. So, you know, one thing that just sticks out to me, and these are two methods here, you don't have to, you know, hold my word to it, but, you know, if you do figure out that that if 15.8% is hydrogen, then the remainder has got to be, the remainder just got to be chlorine. So if you do 100 minus 34 point, or actually we're in the last one here. So if you do 100 minus 15.8, you will in fact get 84.2%. And so you're just saying that, okay, well, 100% minus 15.8% is 84.2%. So if 15.8% takes up this portion of 100%, then the remainder of that has got to be the other element, which in this case, of course, is chlorine. And then, I mean, at that point, you know, you have the mass of hydrogen. But so at that point, you have two percentages, right? I mean, you have 15.8%, and you also have you know, your mass of chlorine, which is 84.2%, and you can sort of do the process that we talked about, which is, of course, looking for, you're making a ratio, you're converting these ratios to their decimals, you're solving for things in terms of one, and you're using your conversion factor to convert from one to the other. So this here I'll leave for you. It's well documented in the previous examples, but the other approach here is, what if it wasn't as apparent to you that 15.8% or that 84.2% is the remainder? What if that wasn't apparent? Well, in that case, I mean, you could use the part over the whole. You could use a proportion, sort of, right? So you have 15. You could use your part over the whole formula. So let me go ahead and write that down. Your part over whole equals your percent number over 100. And so your part in this case would be 0.2604 over the whole, right? Which you don't know, which you probably want to solve for. Over the percent number, you know how much, so this is hydrogen here, right? 0.2604 is hydrogen. And you know how much that translates into percent, right? That's 15.8%, but you want to, again, use the number. It's 15.8% over 100. That's always an indispensable part of this formula. Rather than cross multiply, because of course you do have a proportion. So 100 and then 0.2604 equals x, and then 15.8. And then of course x, which is of course your total in this case, is going to equal everything that we had here divided by 2604 divided by 1.58, or I think it was 15.8. It is 15.8, so 15.8. And if you were to do that, well, you'd get a particular answer. You'd get, I think you'd get 1.64. So you're dividing this by this, and then so your total would be 1.64 grams. And then so it makes sense that, okay, well, I had hydrogen as being 0.2604 grams of hydrogen, plus an X amount of chlorine, right? And that essentially equates to the total amount, the samples added, which in this case we said was 1.64 grams. And so it makes sense. It stands to reason that the amount of grams you'd have in chlorine would essentially just be 1.64 grams minus how much hydrogen took up, which is 0.2604 grams. And then chlorine, the amount of chlorine in grams, would essentially come out to being 1.37 grams, that is. And so you'd have about 1.3. And so, now that you have your now that you have your mass for your chlorine, you could just say that, okay, and you have the total. So you have the chlorine, you have the total, and you have the mass for chlorine. You could just say, okay, well, what percent of the total is chlorine? So what percent of the total? So what percent of the total? And the total I think we discussed was I think it was, let's see here. I think that was a previous example in that case. The total was 1.64, I believe. Let's see, right. What percent of 1.64 grams is chlorine, which we said was 1.37. So what percent of 1.64 is 1.37? Now, of course, you could do the part over the whole bit, but once you really get used to it, you want to take the total, 1.37 over 1.64 and multiply that by 100. What really is going on here? Well, you're saying that you have this much out of this much, and you want that in terms of percent, and then so you multiply by 100 to get that percentage there. And of course, you could do the part of the whole, but eventually you'd come about to the same amount of percentage that we have for chlorine, which is 84.2. Or if you want, what percent of this is that? So you have a part which is 1.37, right? Of 1.64 equals the percent. You're now solving for the percent over the indispensable part of the formula, which is 100. And then, of course, you'd cross multiply and you'd get 1.37 equals 1.64 times x percent. And you're solving for x percent, and then you'd get 100 or multiplied to 1.37 over 1.64. And then, of course, once you get through this entire application here, you'd arrive yet again at 84.2.